Hi, and welcome to Integrating Vast Data AIOS with Kubernetes. When you think about the vast AI operating system, just like a traditional operating system, it encapsulates different pillars. The first one that we've introduced was the data store. It's a universal storage infrastructure that provides you storage access via NFS, SMB, F3, VAI for VMware integration, CSI for Kubernetes integration, and also block access protocol, which is going to be the focus of this demo using NVMe TCP. It is also providing you the vast database, which provides you support for transactional and analytical databases such as Kafka, Python, Parquet, and SQL running directly natively on the vast AI operating system itself. It is also providing you the vast data engine, which is itself divided into the vast agent engine, which provides you the ability to run agentic AI directly on the underlying data platform itself. The insight engine, which provides you to run real-time RAG and embedding microservices on the platform itself. And lastly, it's also providing you the vast data space, which really gives you a globally distributing data computing that you can spread your data across on-premises and off-premises, etc., etc. So let's now talk about Kubernetes. Kubernetes is really the foundation for every modern AI workloads. Every traditional or next-gen AI models, they're all running inside of a container, and the entire thing is orchestrated by Docker and Kubernetes itself. So let's take a look at some of the offerings themselves. Some time ago, NVIDIA released the NVIDIA NIM, which stands for NVIDIA Inferencing Microservices. It basically means that every pattern, every package NVIDIA preset workloads can run inside of a container, so it saves you, the customer, the need to download it and check them for malware and also be up to date manually yourself, all in a pre-packaged Docker container itself. Now, you can run the NVIDIA NIM on a desktop, server, or you can also run the NVIDIA NIM directly on the vast AI operating system itself. As mentioned before, we will also provide you the vast agent engine on the array itself, which not just gives you the ability to run the NVIDIA NIM microservices, which are already available today, but also agentic AI and agentic AI blueprints directly on the vast AI OS itself. And for the focus of this demo, we're going to talk about the integration of Kubernetes, the orchestrator of multiple hosts that can run on the customer external host and in the future directly on the vast AI OS itself using the CSI plugin. CSI stands for Container Storage Interface, and it's basically the interpreter, if you will, that gives the data platform access to data that the Kubernetes host can then access in return and serve those workloads. Okay, so the first thing I'm going to do is create the kubectl namespace in the vast CLI, which we just did. Now we're going to create a secret file. There are two ways to create secret files here. This one is the unencrypted file, and I'm also going to show you the encrypted version later on. So this one is the old way, again, not recommended, but still available, the unencrypted secret file, which we just created, the YAML file configuration itself. And now what we're going to do is to install all the CRDs that are needed, things like snapshots, etc., which are all available in the documentation, so you can literally just copy paste them and it will install the CRDs for you. We can now go ahead and see what is actually running, and the fact that the secret file is being configure the Helm repo to the namespace, etc., which we just added. And now what we're going to do is to actually create the YAML configuration file. So what we need to do is to create not just the namespace, but the policy view itself, which is also known as views within the vast AIOS user interface. So here you can see that we didn't configure it yet because we want to go ahead to the AIOS operating system, which we're just going to do now. And for this specific use case, we're going to use the block protocol using NVMe over TCP. So we're going to go to the element store UI and create us a new view policy. So let's go ahead and create a new view policy. We're going to choose the tenant, the path that is available for this specific file system, even though we're using a block protocol here. the directory, the policy view, whether it's the default one or a new one, and of course selecting the protocol itself, which is here going to be presented using the block protocol. So let's go ahead and click the OK button. We created a new subsystem with the number 868, which we're then going to use in the YAML configuration file itself. So let's go ahead and modify this configuration file to contain this specific subsystem. Let's change it to 68, and that's about it in the configuration file itself. So now we're going to go ahead and check whether the installation is fine and whether those ports are not being bring up using the CSI plugin itself once we apply the YAML configuration values file. So there you go, you can now start query the cluster pod status itself. We also pointed to using the snapshot CRD that I mentioned before. And let's check the status of the pool itself, the pod itself. It's probably going to take a couple of seconds for everything to be bring up as usual in Kubernetes. And you can see now it's being created, and surely it's going to be up and running within a couple of seconds. Now let's go ahead and create a secure token. So here I'm logging into the VAST cluster as the manager. I'm running the list command, and I can see the users that are enabled, and I'm going to create a token for the CSI admin user, which is a user in the same cluster. It's not a separate tenant, that's a separate topic. And so I'm going to create the API token command, give it a name to the token itself, who's going to be the owner of this token, and there you go. You see that the token is being created. And now that CSI admin user can actually go ahead and use the token, which is what we're going to see here, to run commands at the cluster itself, and of course to be used by the Kubernetes pods to get access to the storage. So I'm exporting the value of the tokens to the Linux environment variables, and now when I run the VAST CLI command, you could see that I could gather some information from the cluster using the token itself, which is going to be the same way that I'm going to carve up data from the Kubernetes cluster itself. There you go. See the users there. Okay, now let's go ahead and actually create our stateful container itself. So I'm going to use here something called scale-pod YAML file, which is going to run a specific container and some load on it. So we will be able to visualize the load itself from the VAST AI OS user interface. So I'm creating the scale-pod's YAML file configuration, which is going to run this specific pod with a specific container in there. And now if I go to the VAST UI itself, to the data flows tab, which is very useful, we can filter it by many things and see which host is running the traffic to which VAST VIPs, etc. Let's filter it to the block protocol. And I'm also going to isolate the specific view to the specific pod that I know that is generating the load itself, so I can view it inside of the user interface itself, which is what you're going to see here exactly. Now what we're going to do is we're going to scale this stateful set to 3 replicas. So I'm going to run the scale command within kubectl, and I want to give it 3 replicas, so you can see the replicas and of course the volumes being created on the VAST AI OS itself, slowly and surely being bring up by Kubernetes itself after the volumes being created. And now let's go ahead, and after we see the containers are up and running, to the VAST AI OS UI itself. And as you can see, the volumes, these 3 volumes has been created, and I can view their performance matrices, and I can also go to the VAST AI OS main dashboard and see total matrices like total bandwidth and IOPS that is running on the system itself. Optionally, we can also take a look at what's running inside of the container itself. When you format a block device in Kubernetes, it can either be formatted as a raw device or with the file system itself, which is what we did here, and the default is XFS. So you could actually take a look at the file system within the container itself and see how it's running and what is it mapped to exactly. Next, we're going to create a clone using the block feature in the VAST AI OS. So as you recall, we've already enabled the CRD during the installation of those CRDs, but now we're just going to enable the YAML file, and this is it. We just created a clone using this specific YAML file. Let's take a look of how it actually looks inside. in the restore file itself. As you can see, it gives you a description of the clone itself, what is being used for, the capacity that's being taken, etc. And now we're actually going to create this restore point that we can go ahead and restore the snapshot or the clone from, and we can see what type of properties it contains, and we can actually take a deeper look inside if we want to, using the description command within kubectl to see what's exactly being processed at the system level itself within Kubernetes. So we can see that the snapshot is being taken, and then a full clone operation is being taken at the array level itself. Here you can see the VAST AIOS user interface itself, the global snapshot clones, which shows you that the snapshot is being finalized with a clone operation at the VAST AIOS itself. And that's pretty much it. This is how easy it is to take a clone of a block device using the VAST AI operating system itself. Now let's go ahead and restore the snapshot that we've applied to the container. So let's run the kubectl command with the get pvc, see that the restore point is actually available at the system itself. Let's log into this specific YAML file and see how it looks like. It shows you the data that it's going to restore, the PVC name, etc., etc. And now let's go to apply this restore point itself. So kubectl create the f prod YAML file. We can see that the snapshot restore has been created, and we can also see the status of how long it's going to mount that specific clone on the target container, that the container is up and running. And we can also log into the container file system itself to view the data that's been restored if we want to. Of course, it will vary between a crash consistent to an application consistent type of a backup. And that's about it. It's all been restored, and we can go ahead and delete the snapshot point if that's what we wish to do. Let's talk about monitoring. You can monitor your Kubernetes infrastructure from the VAST AIOS data flow tab itself, and of course from the main dashboard as well. But it's very common that in Kubernetes environments, the kube admins will be using Grafana and Prometheus to monitor your Kubernetes health state. That includes the VAST AIOS components, but also some other components that can be related to networking, application, etc., etc. So here you can see our Grafana reporting pack that I've already installed and configured, and you can view metrics at the AIOS cluster level, cluster statistics level itself, whether it's healthy, how many C nodes are running, things of that nature. And of course also metrics that are related to the specific volumes data themselves. In this case, we're using a block device using NVMe over TCP, so you can also monitor those specific metrics as well.